I'm Jared from the Lazer Robotics, and our team just finished our rookie season in FTC. We had an amazing first season, achieving FAC at our state competition and being invited to MTI. Our best OPR was around the top 1% of teams worldwide. This video is meant for teams just starting out or looking to gain some beginner experience in designing and building an FTC robot. We're going to share our rookie year experience building this robot, the things we did well, the mistakes we made, and things we wish we could have done differently along the way. Hopefully, after watching this video, you can avoid some of the mistakes that we made and speed up your own FTC season. First, I'm going to highlight some of the good things in this robot, and then I'm going to highlight some of the improvement opportunities we discovered after competing against some of the best robots in the world. The first nice thing about this robot is the height of the robot. It fits under 12 inches, which means it can maneuver around any part of the field in this year's game, center stage. This was particularly important, but in international competition or high levels of competition, it wasn't really a great advantage. But in local levels, it was a key feature that allowed us to that gave us a lot of maneuverability. Because of the way the robot was designed, it's extraordinarily difficult to break, so it's really durable. This means that one important thing in FTC is that as your robot's driving around, you're in the heat of a match, robots are going to collide. Whether you expect it or not, you're going to get hit by other robots. So one of the key features of this robot is how durable it is, its ability to withstand hits from other robots from all directions and not break. Because we transitioned out of FLL, we knew durability was kind of important, but we kind of underestimated how important it was in FTC. So that's one of the big things we learned. Another thing is because of how simple this robot is, it's really durable as well. So going into simplicity, you want to design a robot that's really simple. So this robot is simple enough to the point where you can pretty much tell how it works just by looking at it. Simple chassis, simple intake, and simple deposit mechanism. So the simplicity of the robot really helps make sure there's less breaking points, so there's less difficult power transmissions, there's not very many gears, and you're going to spend less time building and repairing the robot to begin with, and it's also going to function more consistently. One more important thing we found throughout the season is the uniqueness of the robot matters a lot. One thing we discovered about this robot is that it's very memorable. So a lot of times what would happen is other team scouts would come and see this robot and be like, wow, I remember this robot. So everything from how you do your number plates to the colors to the overall design and shape of your robot, it's going to feed into how memorable your robot is, which is actually really useful in FTC competitions. Now let's talk about some of the ugly things in this robot. One of the biggest challenges we had with this robot is that it's really heavy. One of the big reasons for that was because of how wide this robot is. So, and one of the reasons why it's so wide is because we didn't really well utilize the space on the bottom of the robot. As you can see, there's a lot of empty space here, that could have been utilized by putting electronics, other motors, and power transmissions. What you'll notice is on some of the best teams in the world, they can utilize the bottom of their robot extremely well, meaning packing all their motors, a lot of their power transmission, and their electronics down there. The other thing this contributes is a lower center of gravity. A lower center of gravity is effective because it can prevent tipping. So that makes a huge difference in terms of the size of our robot, which is one of the big challenges we faced this season. On top of our size, our chassis, there's some additional space in there that could easily be shaved down had we known that we could have done this earlier in the season. This could have saved us maybe 1 or 2 inches, which might not seem like a lot, but in the heat of a match, when you're driving quickly or during autos, that collision will waste about 5 or 6 seconds of your time, which could be an entire cycle depending on the game. So that 1 or 2 inches could be a crucial decision in terms of a match. So that was one thing we really struggled with. One additional thing was how sensitive our robot is to electrostatic disconnect, or ESD. So ESD is essentially just how much static electricity runs through the entire robot as the robot's driving. So things that contact the ground like friction from the wheels, odometry pods, side plates even that are digging into the tiles, all of that will contribute to how much static electricity is running through the robot. So when it gets to a certain point, that static electricity will eventually just enter the hub, and it will cause the hub to actually temporarily disconnect for a second, which could lead to robots just being, immovable, so you can't really control it for around 30 seconds to a whole minute, which is obviously not something you want. We learned about this halfway through the season, which was very, very late, and to be honest, we haven't fully found out why we still have ESD issues. We did, however, discover that some fields are more sensitive than others. And most official competitions we went to, it wasn't really a big issue because of the amount of staticide they sprayed, and it was on a conductive ground surface. So we found that on concrete, on stages, our robot actually performed quite well. But in other places with carpet flooring, plastic flooring, it didn't perform quite as well because it disconnected more often. So teams should know that this can happen really often, and it's something that you should definitely think about as you're designing the robot. There's also kind of no way to get rid of ESD. It's kind of just how can you mitigate it throughout the season as it goes on. Now I'm going to go more in depth into each component on this robot. Before I do that though, the first thing you might notice is a lot of our robot is made out of custom machined aluminum parts. Although we found this to be the best way, it might not be the best in terms of how you choose to design your robot. Some of the best teams in the world actually don't use any custom parts and rely solely off of kit parts to design a robot, and can still be extremely effective with that. Now moving on to the chassis of our robot. Our robot features a 4-wheel Mecanum chassis, and we chose Mecanum because of the balance between speed, maneuverability, and simplicity, compared to a 6-wheel drive or even a swerve. So we also chose to do a belt-driven chassis because of its simplicity and flexibility with where you place the 4 motors. So one of the big reasons for that is obviously you get the flexibility. It's also very consistent, meaning the belts don't skip, especially if they're properly tensioned. The belts really never skip, so they're really, really solid. One big downside is that you have to buy the exact size of the belt. So what will happen is you usually buy like maybe, let's say, 7 different sizes in one order. So belts can be a little bit more expensive, a little bit more might consume a little bit more resources. So that's a big downside to it. One story we have is that we actually redid our drivetrain halfway through the season, and we realized that we were short of the one size belt that we didn't actually order. So that's something that could happen to you if you choose to use a belt. As I said, belts don't skip. The other reason we chose to do belts was instead of like a chain drive or like a gear drive, belts are much smoother and a lot quieter. So chain drives require lubricant to function, and they're also really, really clacky. With gears, obviously gears, it's direct contact, so it's obviously going to be less, it's going to be more rigid, it's probably going to be a little more loud, and gear drivetrains just really are not that popular in FTC. A mistake we made was choosing a live axle setup over a dead axle setup. So we have bearings here, and that was something we realized halfway through the season that we could have done. So essentially what a dead axle setup is the axle itself doesn't actually move, and the wheel rotates around the axle. How we have it set up is that the whole thing is one rigid axle, so it rotates around these bearings here. So that adds some greater mechanical complexity that could have just been eliminated using a simple dead axle setup. So obviously that's something we can look to for next season, and it's also one of the big things we wish we had done with our drivetrain. So now I'm going to take you through the journey of how a pixel moves through a robot and ultimately scores on the backdrop. So at the beginning of the season, and actually for most of the season, we use surgical tubing like this to help control the pixels and sweep them up our intake ramp. These were really effective, and they were really easy to customize and easy to replace. Just simply cutting the tubing was enough. But they were also really messy in terms of how they intaked, and what we found out was all of these are different. So like the flexibility and how it bends over time. So that led to a lot of inconsistencies with sort of how our intake worked. So through that, we found out that over time these break, they have to be replaced. When you replace them, they end up being cut to different lengths, which actually makes a big difference. And the grip and flexibility of these will change over time, which is one of the big problems we found with them. So towards the second, like sort of the off season of this robot, we switched to Go-Builder boot wheels. These were really effective. We found them much, much more effective. They had more grip, and they also have a little hook on the end of them that helps grip pixels. So this is how our robot intakes the pixels. So it rotates, and the pixels go up the ramp like that. So one of the key things that we have is 4 stages of them, and these are all driven with one motor. So 4 stages of the intake, 1, 2, 3, 4, all driven by a motor inside of this box. And what you'll notice is that these are all driven with belts. So we found these to be a really easy way to transmit the power to our intake. It helps make it so that the design was really simple. We could power all 4 with one motor, which was really advantageous in terms of space and motor saving. And it also just allowed us to power the whole intake, which was really important. And one thing you might notice is that some of these boot wheels are different. What we did was we printed these in TPU, which is a flexible 3D printable filament. So what we realized was GoBuilder only makes boot wheels in 3 sizes, which wasn't enough for our use case. So we custom printed our own, which ended up working super well for us. They had enough grip, were the perfect size for how we wanted to function our intake. One drawback, however, was that because it's squishy, it has to be able to take the full force of the shaft rotating around it. So what we had to do was we had to design these in a different material, things that were able to lock onto the boot wheel and didn't allow it to freely rotate without motor power. So then we used a combination of PLA and TPU to be able to securely mount them to this axle so that it could rotate with the entire design. Another thing you'll notice is this one individual printed boot wheel in the front row. So the thing about that one is that it's slightly larger than the rest, which allows it to grip onto a pixel like this, which is especially effective during auto. So that allows us to control the pixel and makes it really easy for us to just drop a pixel on the spike mark, which is what was one of this year's tasks was. And because it's flexible, it still allows us to intake through this wheel, obviously. So that was a really big breakthrough we had. Another thing you'll notice is the top part is actually a wheel instead of a boot wheel. So we made this design choice after realizing that because of its an active intake, pixels move through it quite fast and quite uncontrolled. So we used these wheels to ultimately sort of control it at the end before it goes into our depositor into the next stage. An additional feature of our intake is that the height is controllable through this linkage in the front. And what you'll notice is this is actually a rigid linkage, which means that it's fully rigidly mounted. Its movement is like fully predictable, and it will respond to any inputs that the servo gives it. So one of the typically with an intake, this is a risky move because the intake is a part that might get hit a lot by other robots from the side, from the front, and typically what this will happen is it'll damage your servos. So what a lot of teams choose to do is a sort of more compliant linkage, meaning there's rubber bands, and if it gets hit, the rubber bands just flex. So we chose a rigid linkage because we thought it was more accurate and it was also easier to work with. And how we prevented any sort of accidental damage to our servos was we designed these little mounts down here at the bottom, which support our intake, meaning instead of the servos flexing, the mounts actually flex. So they're little aluminum tabs that are meant to break instead of the servos breaking, which was really crucial to how our intake functioned throughout the season. I think in several of our last competitions, they took massive hits and none of them really did anything to the intake. It still functioned fine at the end. One more feature about our intake is this counter roller down here, which kicks pixels off the ground and onto the intake ramp. This is really important because the hardest part of an intake is just getting the pixel off of the ground and into the robot. So after the pixels move through our intake, they enter our depositor, which is essentially a bucket mounted onto a set of vertical slides. So our slides are cable driven, which means that they use a cable to move around, and these are Mizumi slides, which is a really popular brand within FTC. So our slides move our bucket up, and this is a virtual 4-bar style deposit, meaning that it swings out like this, and this angle is parallel to the backdrop, which makes it really easy to drop and reduces the need for complexity. So essentially just this movement alone is taken care of by one single servo, which is really, really crucial to how simple our robot is. It's also really crucial to make sure our deposit never really breaks. And the way it works is essentially as the pixel falls inside of here, there's a wheel at the bottom that rotates and it spits it out like that. So it's a really simple deposit, although this took us, I think this ramp here took us nearly 20 iterations to get right. So although it seems simple, it took a lot of iterations to get right. And this virtual 4-bar design was an idea that I think we had a couple months into the season. It took a lot of testing with other ideas like claws to eventually reach this state. One key feature about this is that it's really rigid, so it's supported by both sides on the slides. It's got a top plate here, and it's also got many crossbars around it. So that ensures that it doesn't break. It's stable, it swings out stably inside of the robot. It just keeps the whole package together. So there's a continuous rotation servo here that powers the wheel that drops the pixels. And another servo here is a micro servo, which actually controls an additional unique feature of our robot. It's a finger that was used to rearrange pixels on the backdrop. So you would stick it in, you could rearrange pixels like so on the backdrop. That allowed us to score more points, optimize some of the maybe mistakes that we make during a match, so it can help clean up things. We had to use it several times in competition, which was actually really fun to see. And the other thing about our slides and lift is that there's hooks on the back of them. So one of the tasks this year was to be able to do a pull-up on the bar, and instead of having to design a whole nother subsystem that just took care of the hanging, we just did it with our slides. We just decided at the beginning of the season, like, there's no point in designing another subsystem. Let's just throw hooks on the back of our slides and see what happens. So this hook generates enough torque to lift our entire robot. And these slides are driven by two 435 RPM motors, which is the reason why they're able to generate that much torque. So a couple things we discovered were that spool size you use to drive the string of your slides is really, really important. So ours are around 30 millimeters roughly. So the larger they are, the faster they'll go, the less torque they generate, and vice versa. And the inside of our robot is actually quite compact with how we packaged our stringing system. So there's a spool here, and retraction spools here, and a spool here. So it's really symmetric as well. Another key thing is that we managed to make fairly large slides fit within the under 12-inch box that our robot had to fit in for this season, which was really important in terms of how we were able to maneuver the robot around while still having fairly large slides on our robot. So the whole process is that the pixel comes up the ramp into the bucket, the slides lift up, the bucket goes out, and they get dropped using this wheel here. And because this is so simple and effective, it has basically never broken this season. And a couple big learnings we had along the way were, anytime you use slides, wiring instantly becomes a challenge. So the way we tackled this was using this almost snake-like system that as you go down, it sort of snakes into the robot. So the way we took care of this was using belt retractors. So like ID badge retractors, which help pull this big cable snake in a certain direction. As you can see, there's many wires up here from the few servos that are up here. And that's one of the challenges we faced this season in terms of how we designed it. And a big feature as to why we were able to iterate so much and change was because of how modular this was. Well, a big reason why is it has, I think, roughly 4 screws to take out the entire system. So which means we could change it ridiculously fast and test many different ideas. I think we tested, several within one meeting, which was really, really cool to see. Yeah, so our depositor, modular, small, simple. That's how it was so effective in competition. So this is what the process of intaking the pixels looks like. So let's say we have 2 here. They go up the intake ramp. A key thing is that our deposit can actually carry 2 pixels at one time. So then the slides go up, the deposit comes out, and this wheel on the bottom here drops things up. So that's the process of how we score pixels. One more thing is that because of our spinning wheel design, we can choose where we put them on the backdrop. So we don't have to drop both at the same time. We can just say, by spinning the wheel for X amount of seconds, a pixel will drop here. We can move a little bit to say like the right and then drop another one. So that allows us to do easy mosaic building and can score in different spots, which makes us very versatile in terms of how we can score. Another thing is with our intake, you might notice not all the space is utilized because it sort of goes up in a V. So using the additional space, we have a spot for our battery and a spot for our camera here, which helps to do the team prop detection during auto. The last key subsystem in the robot is our drone launcher. So our current drone launcher is a single piece of plastic on the robot, but before we got there, we tested many different ideas. So at the beginning of the season, we played around with flywheel prototypes, which we quickly realized was not the correct move to do because of simply it required another motor and it was overcomplicated. So then we focused on using rubber band power. So at an early season, we used rubber bands in sort of a case like this. It was attached in a similar spot to our robot and used rubber bands to propel the plane forward. While it worked, it wasn't the most consistent and it didn't work the best. An additional thing we experimented with was actually putting the drone launcher on top of our slides. So when we shot, it was actually lifted and we can shoot over the truss instead of having to shoot in sort of parabola style motion over the truss. That it worked well, but it still wasn't quite the consistency we were looking for. Then we decided to test out springs. So these are large extension springs inside of our current drone launcher, and the biggest difference we discovered was that it actually doesn't wear out like a rubber band. So one of the big challenges we had with rubber bands was we essentially had to be like 2 seconds before the match starts, okay guys, load the rubber band now, so that the longer it sits in there, the longer it will begin to degrade, the longer it will begin to just lose some of its tension. The other thing is just due to manufacturing, not all rubber bands have the same tension. So springs fully eliminate that problem essentially. They don't really lose much tension over time, and they can be stretched out for long periods of time and still return the same amount of force to propel the plane forward. So we found a lot more consistent Zone 1 launches with this drone launcher style than we did with any sort of rubber band. So the way this works is essentially we have a loader device because of how the paper airplane device is sort of tucked inside of our robot. So we essentially pull the springs back, it locks into place, and then there's a servo, tiny servo, another micro servo, that when you push a button on the controller, it triggers it. And then let's say I have a drone in here, right? It triggers it, and then it will launch the plane like that. So this is our current drone launcher. We found it to be really, really successful. And it's also ridiculously simple as well. It's literally one single 3D printed body component with springs and a servo attached to it. So this is our drone launcher and how we were able to achieve a pretty solid end game at the end of the game. So on our end game, obviously, as I mentioned, our hang is on the back of our slide, and this is our drone launcher. So it helps us achieve 2 of the end game tasks, get full end game points quite effectively. Now that I've covered each major subsystem on our robot, now I'm going to go into more details about any sensors and cameras that we use that help aid our software throughout the season. So the first major thing is we have one camera here, which was obviously used for our team prop detection at the beginning of each auto. But an additional features, we actually have a hidden back camera here, which was used to detect April tags on the backdrop. So what that allowed us to do was relocalize to help the robot align with the backdrop, which was especially important during long autos in which odometry could drift over time, or you could lose track of where you are on the field. So these 2 cameras helped a lot during auto. One additional thing is our odometry system. So our robot has 3 odometry pods, and these odometry pods essentially, odometry is a way of localizing an FTC. So it uses encoders with dead wheels on them, so meaning they have no motor power, and using some trig and some math and reading the encoder counts off of these, you can figure out a coordinate as to where you are on the field. So we used a path planning, or point-to-point controller system, and written by team 14496 Roboctopod. It's called Cuttlefish. It was really effective. We used it a lot this season, and it was one of the reasons why our autos were so effective. Odometry allows you to sort of plan paths, and it also allows for dynamic error correction. So let's say your robot was pushed off of its path, it can auto-correct back onto the path during auto. So odometry is an excellent way to go about autonomous navigation. So along with our cameras and odometry, it allowed us to have really quick streamlined autos, which were really important. One more unorthodox thing we did was read the motor current being pulled off of our motors. So that could detect, let's say, one way we used it was when the robot was backing against the wall. So if it hit the wall, the motors would stall, they'd pull more current. We could read that current and say that, okay, the current has spiked, we're probably hitting something. So that means we've hit a wall or something like that. So that helped us a lot with how we do our autos. We also have an additional brake beam at the top of our intake. So one of the big challenges we had was how do we make sure we don't over intake during auto. So we installed a brake beam sensor up here, which is similar to the garage door sensor. So it detects if a person is walking underneath. It's really similar in this case. So the pixels go up the intake, it will temporarily break the beam for a second. And that one beam will know, okay, now I know something has broken the beam, it is a pixel. We now know we have 1 pixel inside of our dropper. So at that point we know, okay, let's turn off the intake depending on how many pixels we want, and it helps us prevent over-intaking during auto, which is really, really important this season. Obviously, we didn't start the season with all these great ideas that we had throughout the season. We started the season with simply prototyping with a strafer chassis. And in fact, it took us 3 months to get our first major breakthrough of how we could intake pixels. So our biggest piece of advice we can give to anybody is iterate, iterate, iterate. A lot of these subsystems on this robot have gone, I think, more than 10 plus different iterations, which is one of the big reasons why our robot was able to reach this state at the end of the season. So iterations and testing and refining were one of the big reasons why this robot was able to be so effective towards the end of the season. I think this is all I want to cover on this robot. We covered most of the important features and aspects to this robot. This robot is nowhere near perfect, obviously. It took us many, many iterations to get to this point, and it involved a lot of testing. Our robot is obviously nowhere near perfect. There's a lot of robots in the world that are better than our robot. With more time, with more experience at the beginning of the season, this robot could be going a lot further than it is now. So I hope this video inspired your team to create a better robot than we did in this rookie season, and ultimately learn from our mistakes, learn from things we discovered throughout the season to create a great robot that will perform well at your next competition. Thank you for watching. If you have any questions, leave them in the comments or email us, and we'll do our best to respond.